Okay. Yeah. So our next speaker is Sumegha Garg. Sumegha is a Rabin postdoctoral fellow at Harvard. She completed her PhD last year at Princeton. Her research spans complexity theory and algorithmic fairness, and today she's going to tell us a little bit about the complexity theory side of things. She's going to talk about the space complexity of the coin problem. So take it away, Sumegha.
Yeah, thanks, Mary, for the introduction. Before I start the talk, I want to thank the organizers for inviting me to talk and for TCS women meetings in general. I still follow some of the advice that I learned from my first TCS women meeting 4 years ago. Okay, so back to what I'm supposed to do. I'll be talking about a recent work with Mark and Orr that settles the space complexity of the coin problem. Oops. Okay, so the coin problem, and in the coin problem, we are given a stream of coins, and we want to distinguish between these two, the two following distributions. In one of the stream, we are given n coins, where each coin is independently biased towards one with probability half plus delta. And in the second distribution, each coin is biased towards minus one with probability half plus delta. And we want to distinguish between these two streams with high probability, say 0.9 probability. So in the rest of the talk, I'll use 0 and minus 1 interchangeably, and both represents the negative bit. Now, what is the optimal distinguisher to distinguish between these two distributions? You just output the majority of the n coins. So if the majority is minus 1, you say that the coins are biased towards minus 1. And if the majority is 1, you say that the coins are biased towards 1. And this distinguisher works for OR delta, which is greater than 1 by square root n. This is because 1 by square root n is the smallest statistically distinguishable bias, as for a lower delta, these two distributions of n coins are indistinguishable, statistically indistinguishable. But one of the caveats for this optimal distinguisher is that it cannot be computed by many natural computational models, such as AC0, AC0 with parity, and so on. Let's just talk about the streaming setting for now. You're given a stream of n coins. Then what one of the algorithms that you can do is you can just keep a track of the sum of the coins, and this requires order log n space. And previous works have shown that this much space is actually necessary to compute majority of n bits in a stream. And then the question, a natural question to ask is, can we distinguish between these two streams with lower space? Okay, so let's see at the first attempt at a low space algorithm. I want to construct a log k space algorithm to distinguish between these two streams that have bias to either towards 1 or minus 1. This algorithm just keeps track of the sum and outputs 1 if the sum reaches k at any point, and outputs minus 1 if it reaches minus k. Computing majority is basically equivalent to letting this algorithm run for k equal to n. Now, this algorithm can actually distinguish coins with bias of omega 1 by k. And a natural question to ask is that, is this the best a log k space algorithm can do, that is detecting a bias of 1 by k? So in 1970, this paper proves that it is, yes, that this is the best it can do if the algorithm is time invariant. That is, it doesn't know what numbered coin it's reading. So remember, let's recall the algorithm from our previous page. That algorithm just it's time invariant. I do not need to know what numbered coin I am reading. I just add to the sum if I see a 1 and subtract from the sum if I see a minus 1. And then this paper says that a log k space algorithm can detect a bias of at most 1 by k. Sorry, at least 1 by k. But the question we ask is that if can low space algorithms do better with an access to a clock that keeps track of the coin number? So the memory required to store which coin we are reading is not counted in our space of the algorithm. Such a computational model is encompassed by a read-once branching program. A read-once branching program is a layered graph where each layer, a layered graph with n layers. Each layer has, sorry, can you see my mouse? Okay. So where each layer has W nodes and edges are present only from between consecutive layers. So each node represents a state of the read once branching program, and the ith layer represents the represents the state the read once branching program can be after reading I bits of the input. So, for example, an edge is present from this state to this state labeled by 0 if if the read once branching program transitions from this state to this state when it reads the input bit 0. So how do we process an input on a read once branching program? We start at this vertex in the first layer, and then we transition through the read once branching program by reading each bit one by one, and we reach a vertex in the last layer. The last layer contains two nodes, one representing the accept state and the reject state. So if a path starting from the start vertex and reading the input X reaches an accept state, we say that the output of the branching program is 1 on that input. And if it reaches a reject state, we say the output is -1. And the why read once branching programs are a good model to consider, because we can these program computational models are meaningful even if the width W is much less than n, which is I think of compare W with the 2 to the memory size of an algorithm. So the main question we ask is, what bias can a width, W length, and read once branching program detect? The algorithm that we considered a few pages before, which just counts up to k or minus k, gives us a 2k width and length read once branching program to detect a bias of 1 by k. But the point is that we can read once branching programs can actually much better. For example, for some values of k, a k and length read once branching program can detect a bias of even 1 by 2. As a teaser, let's look at this tripes function. So this tripes function, what the tripes function does is it takes an n-bit input, it divides the n-bit input into n by m blocks of m sized, and it takes the and of each of these blocks, and then it takes or of the output of or of the n by m output of the and functions. So this is a read once formula, which is an or and tree, where the fan-in of or is n by m and the fan-in of and is m. Think of m as approximately log n. So why is this tripes function useful? It is because when each bit of x is 1 with probability half plus 1 by log n, then we know that the output of fx is 1 with high probability. Similarly, if each bit of x is biased towards 0 with probability half plus 1 by log n, then the output of this output of f is 0 with high probability. This means that this read once Boolean formula can detect a bias of half plus 1 by log n, either towards 1 or 0. This is useful because read once Boolean formulas have low width simulation using read once branching programs. So just this tripes function implies a width 3 length and read once branching program that detects a bias of 1 by log n. Uh, just just to understand, like appreciate the strength of this read once branching program, compare it to a time invariant algorithm that can only detect a bias of constant with the constant memory. So, and next I want to just illustrate this simple with three read once branching program that computes the tribes function for some intuition of how ROBPs are useful. So this is a with three read once branching program, and we divide each layer into three colors: one brown, one red, and one green. So we start at the red branch, and then we for the next m input bits, whenever we see a zero, we transition to a brown node. So this means that the AND of this block of m bits is zero, and if we end up at a brown node at the end of m steps, we know that the AND of the previous block was zero, and so we still need to compute the AND of the next block, and then we transition to the red node. And if we after m steps we are still on the red node, this means that the AND of this m block input was one, and the output of the entire tribes function would be one, and thus we transition to the green node. So from the green node we just reach the accept state, and from whenever we are in the brown node, we try to compute the AND of the next block again. So this algorithm uses the fact that we know when the m steps are ending. And that means that there is a clock that tells us that next you are going to read the m plus 1th bit. Okay, so this is my last slide. And now I want to summarize the previous works and our result. So using recursive tribes, recursive tribes, we can get actually a constant with three read once branching program that detects a bias of 1 by log to the constant. And the lower bound here is trivial, as it's just you need a constant with read once branching program in any case. So, and then actually using read once using a and or tree of fan in 2, we can actually detect a bias of n to the minus 0.3 with just log n depth. This is a read once Boolean formula that detects a bias of n to the minus 0.3. So this gives an order log n with read once branching program that detects a bias of as small as n to the minus 0.3. This is compare this to the fact that counting takes n width in read once branching program. We improve this upper bound to detecting a bias of n to the minus 1 by 3. This improvement is interesting because of two reasons. The first reason is that this goes beyond bias amplification properties of read once Boolean formulas. And the second is that we actually give a batching lower bound saying that to detect a bias of anything smaller than n to the minus 1 by 3, you need a polynomial in n width. Such a lower bound was only known for n to the minus half previously. Okay, thank you. And email me to chat about research or any, I don't know, anything in life.